So mechanical equilibrium is in the context of mechanics and physics. Chemical equilibrium is in the context of chemistry and balancing chemical equations. And thermal equilibrium is in the context of thermal mechanics or thermodynamics. And it always implies balance of some sort. Equilibrium of a particle requires a balance of forces, i.e. zero net force, to be acting on the particle. Therefore, the vector equation of equilibrium of a particle is as follows. Here it is, super important equation, the basis of all of statics. So summation F is the total force, the net force or the resultant force, the summation of all forces acting on the particle, which as we know from Newton's second law of motion equals ma, mass times acceleration. That must all be equal to zero for us to have actual equilibrium of a particle. Here, the net or resultant force, summation F or F sub r, is a vector quantity, we're seeing it in bold. Mass of the particle m is a scalar quantity with no direction, and acceleration a is a vector quantity, shown in bold. To apply the equation of equilibrium, all forces that act on the particle must be taken into account. To do so, we must construct a free body diagram of the particle. This is always required. If we're going to ever use the equation of equilibrium, we must first draw a free body diagram. A free body diagram, or FBD, is a drawing of a particle that includes all known and unknown forces that act on the particle. The diagram shows the particle isolated or freed from its surroundings, thus the name, thus including only the particle itself and the forces that act on it, excluding any other details that are outside of the particle itself, so not showing anything else, just the particle itself and the forces that act on it. Cables often pass over pulleys, like this one here. A pulley serves to change the direction of the force within the cable. So cable pulley systems are useful for changing the force, or changing the direction of the force, I should say. And we see a lot of these in our problems. If a particle rests on a smooth surface, like say this particle here, this little object that we can represent as a particle, resting on a smooth, frictionless surface, then the surface exerts a force on the particle that is normal to, which means perpendicular to, the surface at the point of contact. This force is called a normal force and often denoted as uppercase N. N for normal force, which means perpendicular to the plane of contact. The diagram at the top right here shows this scenario visually, what it looks like if you're actually looking at it. Okay, this little particle resting on a smooth surface and also held in place by some tensile force, maybe from a rope and someone pulling on the rope, keeping it in place. And this is a free body diagram, FBD, of the particle, showing nothing else around it, just the outline of the object or the particle itself, and acting at its center, all three of these different forces, where we have T, this is some externally applied tensile force at a 20-degree angle. The weight of the particle is taken into account here. And remember, particles may or may not have mass. We do sometimes neglect the weight of particles, but if we were to take into account the weight, then it would act straight down toward the center of the earth. And the other third force we would have to take into account would be the normal force acting up and to the left on this particle. Okay, this normal force vector N is perpendicular to this plane. And there is some geometry that you could go through, or some trigonometry. Maybe on paper, this would be a good idea to do right now. Pause the video and do this. If this angle of the incline is 30 degrees, you should be able to prove to yourself that this angle that N makes with respect to this vertical line is also 30 degrees. A coplanar force system is a system in which all the forces lie in a single plane, such as the xy plane for these forces shown below. These types of problems are two-dimensional problems. So let's first recall the general vector equation of equilibrium. So we have the net force, which is a vector. The resultant force, we can call it, that equals zero. That is what we require to be true to have equilibrium of a particle. So in Cartesian vector notation using I hats and j hats, that states that the summation f sub x times I hat plus summation f sub y times j hat must equal zero. For this vector equation to be satisfied, the x and y components of the resultant force must both be equal to zero. Thus, the scalar equations of equilibrium for a coplanar force system are as follows. The net force in the x direction must be zero, and the net force in the y direction must be zero. Remember, the net force in the x direction is defined as the summation of all the x components of forces. The net force in the y direction is defined as the summation of all the y components of forces. A three-dimensional force system, as opposed to a coplanar force system, is a system in which not all of the forces lie in a single plane. These types of problems are more complex three-dimensional problems. Thus, the scalar equations of equilibrium for a three-dimensional force system are as follows. So now we have a third equation as compared to the scalar equations we had for a two-dimensional scenario. We now have three instead of two, where the net force in the x direction must equal zero, the net force in the y direction must equal zero, and the net force in the z direction must equal zero.